Hi, I am Ilan Turing. Today I am going to teach you about the progression of AI to where we are today. The perceptron was invented by Frank Rosenblatt in 1957. Rosenblatt was a psychologist who was interested in studying how the human brain learns. He believed that the brain could be modeled as a network of interconnected neurons, and he set out to create a simple model of a neuron that could learn to classify binary data. The perceptron is a simple model of a neuron. It has two inputs and one output. The inputs are multiplied by some weights, and the sum of the products is then passed through a threshold function. If the sum is greater than the threshold, the output is 1. Otherwise, the output is 0. The perceptron can learn to classify binary data by adjusting the weights on its inputs. The weights are adjusted based on the results of the perceptron's predictions. If the perceptron makes a correct prediction, the weights are left unchanged. However, if the perceptron makes an incorrect prediction, the weights are adjusted so that the perceptron will be more likely to make a correct prediction in the future. The perceptron was a major breakthrough in the field of artificial intelligence. It was the first model of a neuron that could learn to classify binary data, and it paved the way for the development of more complex neural networks. The perceptron also inspired other researchers to develop new models of neural networks, and it helped to spark the interest in artificial intelligence research. The perceptron is a simple model of a neuron, but it has had a profound impact on the field of artificial intelligence, which is the foundation of more complex neural networks, and it has inspired other researchers to develop new models of neural networks. The perceptron is a reminder that even simple models can be powerful tools for learning and understanding. Multi-layer perceptrons were introduced in the 1960s by a team of researchers led by Marvin Minsky and Seymour Papert. Minsky and Papert were inspired by the work of Frank Rosenblatt, who had invented the perceptron in 1957. However, Minsky and Papert realized that the perceptron was limited in its ability to learn complex functions. They showed that the perceptron could not learn the XOR function, which is a simple function that is not linearly separable. Multi-layer perceptrons overcome the limitations of the perceptron by adding more layers of perceptrons. Each layer of perceptrons takes the output of the previous layer as its input, and the output of the final layer is the output of the multi-layer perceptron. This allows multi-layer perceptrons to learn more complex functions that are not linearly separable. Multi-layer perceptrons can be used to classify complex data by adjusting the weights on the connections between the perceptrons. The weights are adjusted based on the results of the multi-layer perceptron's predictions. If the multi-layer perceptron makes a correct prediction, the weights are left unchanged. However, if the multi-layer perceptron makes an incorrect prediction, the weights are adjusted so that the multi-layer perceptron will be more likely to make a correct prediction in the future. Multi-layer perceptrons have had a profound impact on the field of artificial intelligence. They have been used to solve a wide variety of problems, including image classification, speech recognition, and natural language processing. Multi-layer perceptrons have also inspired the development of other machine learning models, such as deep neural networks. They have been used to solve a wide variety of problems in the field of artificial intelligence, and they continue to be an active area of research. Feed-forward neural networks (FNNs) were introduced in the 1980s by a team of researchers led by David Rumelhart. FNNs are a type of neural network that allows for the processing of more complex data than traditional perceptrons. This is because FNNs have multiple layers of nodes, and the connections between the nodes are not all direct. FNNs work by having nodes in each layer that are connected to nodes in the next layer. The connections between the nodes are weighted, and the weights are adjusted based on the results of the FNN's predictions. If the FNN makes a correct prediction, the weights are left unchanged. However, if the FNN makes an incorrect prediction, the weights are adjusted so that the FNN will be more likely to make a correct prediction in the future. FNNs are a powerful tool for processing complex data. They have been used to solve a wide variety of problems in the field of artificial intelligence, and they continue to be an active area of research. In the early days of artificial intelligence, neural networks were limited in their ability to process sequential data. This is because traditional feed-forward neural networks can only process independent data points. However, sequential data is often interrelated, and this can make it difficult for traditional feed-forward neural networks to learn from it. For example, consider the task of predicting the next word in a sentence. A traditional feed-forward neural network would need to see the entire sentence in order to make a prediction. However, this is not always possible, as we often only have access to a few words at a time. To address this limitation, researchers began to develop architectures in which not every node directly feeds forward to all nodes in the next layer. These architectures are called recurrent neural networks (RNNs), and they allow for the processing of sequential data. RNNs work by having connections between nodes in different layers that allow information to flow back and forth. This allows RNNs to learn long-term dependencies in data, which is essential for processing sequential data. RNNs are a type of neural network that is specifically designed for processing sequential data. RNNs work by having connections between nodes in different layers that allow information to flow back and forth. RNNs can be used to learn long-term dependencies in data, which is essential for processing sequential data. RNNs have had a profound impact on the field of artificial intelligence, and they continue to be an active area of research. Even after the introduction of RNNs, neural networks were limited in their ability to process natural language. This is because traditional neural networks are not able to learn long-term dependencies in language. For example, consider the task of machine translation. In order to translate a sentence from one language to another, a neural network needs to be able to understand the meaning of the sentence in the original language and then generate a sentence with the same meaning in the target language. However, traditional neural networks are not able to do this because they can only process the sentence one word at a time. To address this limitation, researchers began to develop architectures that are specifically designed for natural language processing. One of the most successful architectures is the transformer architecture. The transformer architecture is based on the attention mechanism, which allows it to learn long-term dependencies in language. The transformer architecture is made up of an encoder and a decoder. The encoder takes a sequence of words as input and produces a sequence of hidden states. The decoder then takes the hidden states from the encoder as input and produces a sequence of words as output. The attention mechanism allows the decoder to attend to different parts of the encoder's hidden states, which allows it to learn long-term dependencies in language. The transformer architecture is a type of neural network that is specifically designed for natural language processing tasks. The transformer architecture is based on the attention mechanism, which allows it to learn long-term dependencies in language. The transformer architecture has had a profound impact on the field of natural language processing. The transformer architecture continues to be an active area of research. In the field of machine learning, there is a wide range of architectures that can be used to solve different problems. Some architectures are relatively simple, while others are very complex. However, despite the differences in complexity, all of these architectures are still used today. There are a few reasons why simple architectures are still used in machine learning. First, they can be very efficient. Simple architectures typically have fewer parameters than complex architectures, which means that they require less data to train and can be run more quickly. Second, simple architectures can be easier to interpret than complex architectures. This is important for some applications, such as medical diagnosis, where it is important to understand how the model makes its predictions. It is likely that the field of machine learning will continue to see the development of both simple and complex architectures. Simple architectures will continue to be used for tasks where efficiency and interpretability are important. Complex architectures will continue to be used for tasks where performance is the top priority. Both simple and complex machine learning architectures have their own strengths and weaknesses. The best architecture for a particular task will depend on the specific requirements of that task. If you like this type of content, be sure to hit the like and subscribe buttons.